Did you know that a single grenade factory can produce over 10,000 units per day, each one capable of creating a blast radius of 15 meters? What you're about to see is one of the most dangerous yet precisely controlled manufacturing processes in the world. One mistake, one wrong temperature, one miscalculation, and the entire facility could face catastrophic consequences. Today, we're taking you inside the heavily guarded walls of a military grenade production facility. You'll witness how raw steel transforms into a weapon that has changed modern warfare forever. And stay until the end, because we'll reveal the most critical and dangerous step in the entire process, the moment when these devices truly become explosive. Let's step inside the grenade factory. Every grenade starts its life as something surprisingly ordinary: sheets of steel and aluminum. These aren't just any metals, though. The steel used must meet military-grade specifications with exact carbon content and tensile strength measurements. A single batch of raw material goes through at least 15 quality control checks before it even enters the production floor. The metal arrives in large coils, weighing up to 2 tons each. These coils are stored in climate-controlled warehouses because even slight temperature variations can affect the metal's properties. Before processing begins, each coil receives a unique identification number that will follow every single grenade made from that batch through the entire manufacturing process. But here's what most people don't know. The metal composition isn't just about strength. Engineers must calculate the exact fragmentation pattern. The steel must be hard enough to create effective shrapnel, but not so hard that it shatters unpredictably. This balance is achieved through precise alloy mixing, and we'll see how that plays out in the shaping process. The raw materials also include components you might not expect: copper for detonators, brass for striker mechanisms, and specially formulated primers that we'll examine later. But first, let's see how that steel transforms into the iconic pineapple shape you recognize. The metal sheets move to the stamping section, where industrial presses exerting up to 500 tons of pressure transform flat steel into hemispherical cups. These machines operate with millimeter precision because the wall thickness must be exactly uniform. Too thin, and the grenade becomes structurally weak. Too thick, and the fragmentation pattern fails. Here's where it gets fascinating. Those grooves you see on a grenade, they're not just for grip. They're called fragmentation scoring, and they're engineered to control how the grenade breaks apart during detonation. Modern computer simulations help designers create patterns that produce consistent fragment sizes, typically between 2 to 5 grams each. The two halves of the grenade body are formed separately, then brought together for welding. This isn't simple welding, though. The seam must be absolutely airtight and as strong as the surrounding metal. Laser welding technology, operating at temperatures exceeding 3,000 degrees Celsius, fuses the two halves in just 2.8 seconds. After welding, each shell undergoes pressure testing. They're placed in chambers and subjected to pressures far exceeding what they'll experience during actual detonation. Any shell that shows even microscopic weakness is immediately rejected and recycled. But remember, at this point, we're still just dealing with empty metal shells. The truly dangerous work is yet to come, and we'll get to that critical final stage shortly. Guys, don't forget to subscribe and like. While the shells are being formed, another section of the factory produces the internal components. This is where precision engineering becomes absolutely critical. We're talking about parts manufactured to tolerances of 0.01 millimeters, about 1/10 the thickness of a human hair. The striker mechanism is essentially a spring-loaded firing pin. When you release the safety lever, often called the spoon, this spring drives the striker into a primer cap. The spring must have exact tension. Too weak, and it won't reliably detonate. Too strong, and it becomes dangerous to handle during assembly. The delay fuse is another marvel of engineering. Most military grenades have a 4 to 5 second delay between lever release and detonation. This delay is created by a precisely measured column of pyrotechnic compound that burns at a controlled rate. The compound is pressed into tiny tubes under hundreds of pounds of pressure to ensure consistent burn time. Here's something that might surprise you. Each delay fuse is individually tested. Obviously, they can't test it with actual explosives. but manufacturers use special equipment that measures the burn rate using sensors and high-speed cameras. Fuses that burn even 0.2 seconds too fast or too slow are rejected. The safety pin and lever mechanism also requires precise manufacturing. The pin must be easy enough to remove when needed, but secure enough that it never comes out accidentally. Military specifications require that pins withstand a pull force of at least 8 pounds before releasing. Assembly of these internal components happens in a separate, climate-controlled room. Workers here often have years of specialized training because one misaligned component could render the grenade either useless or unpredictably dangerous. The explosive compound used in most modern grenades is a precisely formulated mixture. Composition B, one of the most common, contains RDX and TNT in specific ratios. This mixture provides the perfect balance of blast power and fragmentation effectiveness. Here's what makes this process so dangerous. The explosive arrives as a heated molten material. It's poured into the grenade shells in a liquid state at temperatures around 80 to 90 degrees Celsius. Workers in this section wear specialized protective equipment, and there are never more than 2 people in the filling room at any time. The molten explosive is poured into the shell surrounding the already installed delay fuse mechanism. The amount must be precisely measured, typically around 180 grams for a standard fragmentation grenade. Too little explosive and the grenade won't fragment properly. Too much creates excessive pressure that could crack the shell. As the explosive cools and solidifies, it must do so uniformly. Air pockets or voids would create unpredictable detonation characteristics. The cooling process takes several hours in temperature-controlled chambers, and each grenade is monitored with sensors. After cooling, the detonator assembly is installed. This is the final component that connects the delay fuse to the main explosive charge. It contains a small amount of primary explosive, extremely sensitive material that initiates the larger explosion. Installing detonators requires specialized training and steady hands because this is the moment when the grenade becomes truly live. To build a finished weapon, the journey of a grenade through the factory takes approximately 72 hours and involves over 200 individual operations. Each grenade you've seen represents the work of dozens of skilled technicians, engineers, and quality control specialists. The modern grenade factory is a testament to precision engineering, where millimeters matter and mistakes simply aren't an option. It's a place where metallurgy, chemistry, and mechanical engineering converge to create one of warfare's most iconic weapons. What started as simple sheets of metal has become a precisely engineered device capable of changing the outcome of combat situations. And now you know exactly how it's made. If you found this fascinating, hit that subscribe button because we're taking you inside more factories where everyday objects are made in extraordinary ways. Next time, we'll explore something even more complex. See you then.